Hi, the purpose of this video is to explain the relationship between average and instantaneous rates of change, how the instantaneous rate of change is the result of a limiting process of the average rate of change, and to specifically illustrate how to compute an instantaneous rate of change by computing a sequence of average rates of change. This video parallels an example in the Rogoski calculus textbook. So I'd like to study what happens when we drop a ball. And we're going to drop a ball at time 0 because that seems like a really good time at which to start the experiment. And we're going to estimate the instantaneous rate of change, the instantaneous velocity of the ball at a particular time, in this case 0.8 seconds. We're modeling the path of this ball with the function s of t. And in this case, it's 4.9 seconds squared, or another way of thinking about that is at 9.8 over 2 seconds squared. Now, we're 9.8 meters per second is the acceleration due to gravity on Earth. So this is just the standard modeling function for an object falling under free fall on Earth. So basically there's a person and they have a ball and the ball is falling and s of t equals 0 is at the top, and then the s-axis gets bigger as you go down. Okay? And we want to find out how fast is the ball falling at time t equals 0.8, question mark. And once we have the tools of the derivative readily at our hands, we'll be able to answer this question more directly. We're working now on the conceptual connection between the limit and the derivative, and between average and instantaneous rates of change. So what we're going to do is we're going to estimate this by computing a succession of average velocities, all rooted at time t equals 0.8. And I'm going to do this by constructing a table. I could easily do this in Excel if I wanted, and then I could just use like the little black cross pull down feature to propagate this as much as I wanted to and do more steps. So that could be really nice. What I'm going to do is I'm going to take as root time 0.8, and I'm going to compute the average velocity for a sequence of delta t values. So the first column I'm going to build in my table are going to be delta t's. And I'm going to start by computing the average velocity when delta t is 0.1. That corresponds to the time interval from 0.8 to 0.9 because the difference between those two things is 0.1. Okay, so I need to know a few things about the position and the time at which the ball was at the position in order to compute this. So I need to know what is s at 0.8, and I need to know what is s at 0.8 plus delta t, and from that I'll compute delta s for the corresponding delta t. Different delta t's lead to different delta s's. So the first thing we need to know is what is the position of the ball at time equals 0.8. Now, I'm a big fan of using the ANS trick in my TI calculator, and I'll do my best to demonstrate that now using my simulated TI calculator in my iPad. So I now have my simulated TI calculator on my screen, and I'm going to use what's called the ANS trick, or at least I call it the ANS trick, to evaluate the function 4.9 seconds squared really quickly for different t values. So what I'm going to do is I'm going to enter in the t value that I want to evaluate my function at first. And I'm going to go 0.8, enter. And now the special ANS variable in the TI calculator is 0.8. And now I can use ANS in place of my variable in my function. And so I want to evaluate 4.9 t squared, or I could go times 0.8 squared. There's a faster way to do it, and that's using the ants trick. So I'm going to go 0.8, enter, 4.9 times ants squared, enter. And I get the same value, 3.136. So I'll enter that into my table. And now I need to know what is S at 0.9 for the next value in my table, because I'm going to go 0.8 and then add 0.1 to it to get to the actual t value for the second point, the secant point on my curve. So I want to go 0.9, enter, 0.9, enter, and then second entry, until I call up that previous thing, and then I can go enter, and it'll tell me what S at 0.9 is. And that's going to be 3.969. Now, I need to know what the difference between these two values is. So that's going to be the entry minus 3.136. Enter. And that difference is 0.833. And then finally, I'm going to enter in delta S over delta T, and that is my average rate of change over that time interval. 0.833 divided by 0.1. And I get the value 8.33 meters per second. Let's see what happens as I take delta t smaller and smaller. As delta t gets smaller and smaller, this average rate of change will turn into the instantaneous rate of change. So I'm going to next go to 0.01. That corresponds to the interval from 0.8 to 0.81, a much smaller time interval, and so we expect it to be a better estimate. This value here, 3.16, this value here, 3.136, didn't change, but now we need S at 0.81. So I'm going to go 0.81, enter, and I can recall my previous values that I entered. So we'll go 4.9 answers squared. And I have 3.21489. Now I need the difference between these two columns, and that goes right there. And so now I'll subtract 3.136. Ooh, look how much smaller that is. 0.07889. And now I take my delta S value and I divide it by my delta T value, and I get, let's see here, so we're just dividing by 0.01, and so I can simply move the decimal place over a few, and I get 7.889 meters per second. So let's see what happens as I continue taking a smaller and smaller value of delta T. Let's go 0.001 this time. Now I can speed up this calculation by using the ants trick, but just kind of combine these three steps right here. First, I'm going to enter my delta T value, 0.001. And now ants is my delta T value. So I'm going to evaluate 4.9 times 0.8 plus delta T squared minus 3.136 divided by delta T. So what I have written there corresponds to 4.9 times 0.8 plus delta T squared minus 4.9 times 0.8 squared all over delta T. And that's just what this last column here asks us to do. So I've got the difference, which is the delta in the delta S. I've got this number here, which is this number. And I've got this number here, which is this number. So if I push enter, now it will compute the next value in my table. And so I know that for 0.001, my average rate of change is 7.8449. Now, using the ANDS trick, I get a really great mechanism for evaluating this expression repeatedly. Say I want to do 0.0001. No problem. I go 0.0001. Enter. Second entry. Second entry. And then I just push enter, and it evaluates it for me. I love the ANDS trick. And I get 7.84049. Let's get off of the powers of 10 sequence a bit. So let's go 0.00005 and see what happens. 1, 2, 3, 4 zeros. And then a 5. Second entry, second entry. Look how fast that makes it. Isn't that awesome? Oh, I love using the ANDS trick. So this is going to be 7.840245. I think I see what's happening. I think this part here is going to 0. Let's do one more in the sequence now that we have a mechanism for doing them really easy. So let's go 0.00000. So let's do 5 zeros and a 1. Okay? 1, 2, 3, 4, 5 zeros and a 1. That's my delta t value. Second entry, second entry. And evaluate it. Oh yeah, look how that tail of that number behind the 0.84 is going to 0. That's so cool. 7.84, 1, 2, 3 zeros, and then a 49008. I'm guessing the stuff back here is starting to become noise. That part there is going to 0, and this part right here is fixed. I think that we can therefore conjecture that the instantaneous velocity at time t equals 0.8 is equal to 7.84 meters per second. I think that process is really cool because it doesn't look at the beginning like there's much of a pattern up here, right? Like, especially in like these first ones here, it's changing a lot. But once we get down to the small numbers, that's where it really starts to jump out. So if you're approached by a problem where you need to estimate an instantaneous rate of change by computing average rates of change, or equivalently, compute the slope of a tangent line by computing slopes of secant lines, they're the same thing, you can just engage in this process. I really like using the ANDS trick as a way to speed up repeated computation of the same function at different points. Makes it really easy. There are other tricks in the TI calculators that make this fast to evaluate an expression over and over as well, that involve plotting it or using a table. Those are not part of this video, but I'm hoping to cover that in other places. Thanks a lot for watching, and good luck. I believe in you.